Welcome everyone to Math Explore Infinity. Today we'll be diving into some essential results about integration and measure theory. So for this particular lecture, we will not be going down the rabbit hole of rigorous theorem proof, right? But fear not. Whenever it is needed, I will drop I'll drop hint on how you can actually tackle those proofs. Again, your engagement is actually vital to me, so please feel free to share your thought in the comments, and do not hesitate to reach out, right, if you need any help. You are not alone, right? So we are in this together. So let's start. Let omega a mu, right? So denote a measure space. I will tell you in a second what it means. Measure space. So this means omega is a set, right? And say number one, calligraphic A is actually a sigma algebra. It's a sigma algebra in omega. So this means A is a collection of subset of omega. Collection of subset of omega, right? Such that say number A the empty set is in the collection, right? So number B, if A is actually in the collection, then the complement is also in the collection. And finally, the collection is actually stable on the countable union. So the union of say n moving from 1 to infinity is actually in the collection whenever an is in A for every n. Okay, so number 2, mu is actually a measure. Mu is a measure. So what does it mean? So this means mu is a map, right, defined on the collection A. To 0 plus infinity, right? And mu satisfies, let's call it A. Mu of the empty set is 0. And we have mu of the union of an, right? N moving from 1 to infinity is equal to the summation over n moving from 1 to infinity of mu of an, right? This is true whenever an and the collection of an are pairwise disjoint. So is whenever n is a disjoint countable family of element of A. Okay, so you should note that element of A are often, are called measurable set, right? And I think for this particular lecture, I think we should, although it is not essential, right? So we should assume that omega is sigma finite. So this means that there exists a countable family, say omega n, right, in A, right, such that a countable family of measurable set, such that omega can be written as the union of the omega n, right, and moving from 1 to infinity, and the measure of omega n is actually finite for every n. So in this case, you say that the set omega is actually sigma finite. Okay, good. The set, let's call it star. So the set, the set, the collection A, right, with the property that that the measure of the set is actually 0, right, are called null sets. Okay, so and again, we say that a property holds almost everywhere, right, or for almost all x in omega, right, if it holds everywhere on omega except on a null set. Okay, good. So for what follows, we denote by L1 of omega mu, right, or simply L1 omega, right, or just L1, right? So this is actually the space of integrable functions from omega into R, right? And we often write the integral of f, right, instead of the full notation, right? And this is let me drag it a bit. This is just to say the integral of omega of f of x d mu x. And also when we write norm of f in L1 by norm of f1, right? So to refer to norm of f in the L1 norm, and this is nothing else following the notation above, the integral of absolute value of f. Okay, so I think we have everything to state our first theorem. So theorem 4.1. This is actually the monotone convergence theorem, also known as Beppo-Levi theorem. So this is monotone convergence Beppo-Levi. Okay, good. So let Fn, right, be a sequence of functions in L1, right, that satisfies the sequence should be actually pointwise increasing up to a null set. So should have f1 less or equal than f2 less or equal than fn, which is less or equal than fn plus 1, and so on. This should hold almost everywhere on omega. And also our sequence is actually how would I write it? The supremum of the absolute of the integral of fn, right? It's actually finite. So then, if you have a sequence of L1 functions that actually satisfies A and B, then Fn converges almost everywhere on omega, right, to a finite limit. So then Fn converges almost everywhere on omega, right, to a finite limit, right, which we denote by f, right? So this means Fn actually converges to f almost everywhere on omega. Then in this case, f is in L1, right, and we even have strong convergence in L1. This actually goes to 0. Okay, so a similar theorem is actually known under the dominated convergence theorem, so theorem 4.2. This is not right, good. Dominated convergence theorem. Okay, so again you have a sequence of L1 functions. So let Fn, right, be sequence of functions in L1, right, that satisfy Number A, right? You have pointwise convergence up to a null set. So Fn actually converges to F almost everywhere on omega. Number B, there exists the function g in L1 such that for every n, the absolute value of Fn of x is actually less or equal than g of x almost everywhere on omega. Then f is actually integrable, f is in L1, and you also have norm convergence of the sequence. Actually goes to 0. So good. So lemma 4.1, and this is actually the famous Fatou's lemma that some of you may know. Let again Fn be a sequence of element of L1, right? That satisfy by A, and for every n Fn is greater or equal than 0, right? Almost everywhere. So they should be positive, right? The supremum of the integral of Fn is finite. So for almost every x in omega, right? So we set f of x to be the lim inf of the Fn of x, right? Which is less or equal than plus infinity. So then, if A and B are satisfied, then f is in L1, right? So the lim inf of the Fn of x is in L1, and the integral of f, right, is less or equal than the lim inf of the integral of Fn. Remember that this is just a short notation for the lim inf of Fn, right? G mu. Okay, so the basic example of a measurable set would be so let me write it. So a basic example of a measure space would be, say, Rn, right? Where this is called, this is the Borel sigma algebra. And this is just the Lebesgue measure on Rn. So this would be a typical example of a measure space. Okay, so let's have some notation first before stating our next theorem. Notation. We denote by CCRN, right? The space of continuous, of all continuous functions on Rn, right, with compact support. With compact support, the support of a function is it's actually the smallest closed set beyond which the function vanishes. So let me just probably, so this is the smallest closed set, right, beyond which the function vanishes. Okay, so to be a bit more explicit, the space CC Rn, right, is equal to the set of functions that are actually continuous on Rn, such that f of x is actually 0, right, for every x in Rn minus k, right, where k is compact. So this space actually is often denoted by d of Rn, the space of test function. Okay, so our next theorem is actually related to denseness, theorem 4.3, I think so. And this is a denseness result. So the space CC of Rn, the space of continuous function with compact support, is dense in L1 of Rn. So this means for every f in L1 of Rn, right, and for every epsilon positive, there exists, say, f1 in the space CC Rn, right, such that the norm of f minus f1, the one norm, of course, is actually less or equal than epsilon. Good. I think probably in our next video we even see that that the space of continuous function with compact support on Rn is even dense in LP, right, for p greater or equal than 1 and strictly less than infinity. Okay, so first thing is to observe is that let omega 1 say a1 mu 1, right, and omega 2 a2 mu 2 be two measure spaces, right, that are sigma finite. Okay, so I mean, what you have to know is that one can define the standard way. I mean, let me just write it. So one can define the standard way. I mean, really standard. The standard way, the structure of measure space, say omega a mu, right, on the Cartesian product omega equals omega 1 cross omega 2. This will not fit. Also omega 2. Okay, so Theorem 4.4. This is about Tonelli. Theorem 4.4. Tonelli, let capital F, right, define the Cartesian product omega 1 cross omega 2 into R, right, be a measurable function. Measurable function satisfying number A, put it in column, the integral over omega 2, right, of the absolute value of f of x y d mu 2 y, right, it's actually finite for almost every x in omega 1. This is 2, okay, good. And B, the integral over omega 1, right, d mu 1 of x of the integral over omega 2 of the absolute value of f of x y d mu 2 y is finite. So if A and B are satisfied, then for a measurable function f, then the function is actually integrable over the whole domain omega 1 cross omega 2. So of course, when we talk about Tonelli, I mean, we see immediately Fubini, right? So sometimes people used to apply the theorem, I mean, without even knowing the assumption. So I was very good into that actually. Theorem 4.5. This is Fubini. Right. It's about how to, when to interchange the order of integration. Assume that f is in L1 of omega 1 cross omega 2. So let me highlight that. So, okay, then put it in color for almost every x in omega 1, right? F of xy is in L1 of omega 2. I mean, I put L1y to say that, I mean, the variable here is actually is y, right? X is actually fixed and y, I mean, actually varies. So this is here, and the integral over omega 2, right, of f of x y d mu 2. I mean, it's actually integrable with respect to x. The element of L1x of omega 1. So similarly, I mean, it also works the other way around. So similarly, for almost every y now, right, in omega 2, f of xy is in L1x of omega 1. And the integral over omega 1 of f of x y d mu 1. This is integrable with respect to y. Okay, so moreover, so this is not the end. So moreover, one has the integral over omega 1 d mu 1 of x, integral over omega 2 of f of x y d mu 2 of y is equal to the integral over omega 2, so of d mu 2 of y of the integral over omega 1 of f of x y d mu 1 of x, which is equal to the integral over omega 1 over omega 2 f of x y d mu 1 of x d mu 2 of y. Okay, so I think we kind of stated already all the some essential properties about integration and measure theory. So now let's have a look at some properties of LP spaces. So let's call it 4.2. So definition and elementary properties of LP spaces. Okay, so we start with a definition. So let's define what LP spaces are. So definition. I think I use the wrong color. So definition. Okay, so let P in R, right, with P strictly less than 1, strictly greater than 1 and strictly less than infinity. So let me highlight that. So we set LP of omega is equals to a set of function f, right, defined from omega into r, right, such that f is measurable, right, and the absolute value of f raised to the power p is actually integrable, right? So I mean, this condition can be written as the integral of omega with the absolute value of f to the power p d mu is actually finite. Okay, so if the following norm, right, associated to the LP, so if the norm, so let me use the norm of f in LP being equal to, I mean, we often write, norm of fp, right, to refer to the LP norm, right, and this is defined to be the integral of omega of the absolute value of f of x to the power p g mu x to the power 1 over p. And of course you can actually check that this is a norm. You can check it. Okay, now for p equals infinity, right, we set L infinity omega to be a set of function f, right, defined again from omega to r, such that f is measurable, right, and there exists a constant c positive, right, such that the absolute value of f of x is actually less or equal than c almost everywhere on omega. Good. So the corresponding norm associated to L infinity is defined to be norm of f L infinity. So you often write norm of f infinity. This is the smallest constant c positive, right, for which the absolute value of f of x is actually less or equal than c, right, almost everywhere on omega. Good. So let's have a remark first. Remark. If f is actually in L infinity, so then we have the absolute value of f of x is actually less or equal than norm of f infinity almost everywhere. Let me drag it for it to fit almost everywhere on omega. Good. You can actually prove it as an exercise if you want. So okay, so notation. So let p between 1 and included plus infinity, right? We denote by p prime. It's often in some book it's denoted by q, right? The conjugate exponent the conjugate exponent of p, right? So this means 1 over p plus 1 over p prime equals 1. So if this relation is fulfilled, then p prime is actually the conjugate exponent of p and vice versa. So our next theorem is actually a very famous theorem, like well known in mathematics. So theorem 4.6. Doing this looks ugly. Theorem 4.6, yes. And this is Herder's inequality. So assume that you have a function f, right, in LP. It's really important. LP, right, and another function g, but this time in LP prime, right, with p between 1 and plus infinity. Then the product fg is actually in L1, right, and the integral of the absolute value of fg is less or equal than the LP norm of f times the LP prime norm of g. Okay, so I mean, just for those who are interested, I mean, the proof of the proof relies on I think it is Young's inequality, right, and the concavity of the logarithmic function. On 0 infinity. So as I mentioned earlier, LP is actually a vector space, and the norm, the LP norm is actually a norm, right, for any p, including p equal plus infinity. So our next theorem is actually the Fisher's theorem. So theorem 4.8. And this is Fisher's theorem. The theorem states that LP and O with the LP norm that we defined above is a Banach space. It's a Banach space, so any p, right? P between 1 and plus infinity. Again, you can actually kind of try to prove it if you want, right? But it is not complicated. So theorem 4.9. So let Fn be sequence of element of the LP space, right? And let F be an element of LP, right? be such that Fn converges to F, right, in LP norm. So that the norm of Fn minus F goes to 0, of course, as n goes to plus infinity. So this is Fn converges to F strongly, right? Strongly in LP. So in this case, then you can always extract a subsequence, right, that converges pointwise, of course, up to a null set. So then there exists a subsequence say Fnk, right, and a function h in LP, right, such that say a Fnk actually converges pointwise to F, right? This is almost everywhere on omega, so pointwise convergence up to a null set. And B, the absolute value of Fnk of x is less or equal than h of x. This holds for all k, right? And for almost every, and almost everywhere on omega. So this actually means that, as I said, from a strong convergence sequence in LP, you can always extract a pointwise convergence subsequence, right, up to a null set, of course. So I think with this, we stop this lecture here, right? And thank you for watching, and see you in the next video.